Sure, why not?
You feel that? That's gas.
Yep, I can definitely feel that.
That is true, and you know why?
Yes, actually.
No, okay. See, gases have small particles that move around rapidly and go crazy, and they are everywhere.
Unlike water, who have particles that slide each other smoothly.
Right.
Or solids who stick together and barely move, basically vibrating.
Oh God, please don't.
Exactly.
Thanks, Denise, that really helped. All this visual learning really helps.
Okay, now let's hear it. We need to turn Celsius to Kelvin. Why? You ask? Because that's one of the rules in order to solve some of the combined gas law problems.
And how do you convert it from Celsius to Kelvin?
How? Well, it's simply you just need to get your Celsius degrees and add 273, and you guessed it, Kelvin.
For those people who don't understand, Marisol.
Hey!
An example is 40 degrees Celsius plus 273 equals 313 Kelvin.
Now, we go to the kinetic theory. It's a study of the microscopic behavior of molecules and the interactions which lead to macroscopic relationships, like the ideal gas law. See, I do know a little bit.
The average kinetic energy is the same for all gases at a given temperature, regardless of the identity of the gas. Furthermore, the kinetic energy is proportional to absolute temperature of the gas.
Absolute temperature of a gas is a measure of the average kinetic energy of its molecules, meaning that if two different gases are at the same temperature, their molecules have the same average kinetic energy.
Wow, good job. Too bad everyone knows that. The molecules in a sample of gas have an average kinetic energy, and the individual molecules move at various speeds.
Anyways, should we talk about something else? This is boring.
Why? Because you have absolutely no idea of what we're talking about?
I do know stuff, but pretty much, yeah.
It's okay, let's just finish this combo first. Then we talk about things you like. You know, like shapes and colors. No offense.
Not taken. I actually don't know half the colors that exist. Like, what's burgundy? That's how you say it, right? Burgundy.
Anyway, where do we stand on STP?
We don't stand on STP. We stand on the ground. Duh, everybody knows that.
Funny, no, but seriously. Let's talk about STP.
Now, we have to know the values and the meaning of standard temperature and pressure, also known as STP. First of all, what's the meaning of standard temperature and pressure?
Well, I'm glad you asked. Not really, but oh well. STP is most commonly used when performing calculations on gases, such as gas density. And where did she go?
She's probably bored or something. Anyway, this is because gases occupy different volumes at different temperatures and pressures. It is necessary to define a set of conditions that can be considered standard form.
The standard temperature values are for temperature. It is 273 Kelvin, and the standard pressure is 1 atm pressure. At STP, 1 mole of gas occupies 22.4 liters of volume as the molar volume. No, not that type of mole. The other one, used in calculations that equals 6.02 times 10 to the exponent of 23. That is what you use when you use the ideal gas law. 1 mole gas has a volume of 22.4 liters, and those are the volumes of STP. Now take that off your face.
Can't I love it? It does not talk about boring science stuff like STP.
That's because it does not talk at all. And look on the bright side. You have both something in common. You both know absolutely nothing. I doubt you both have brains.
Exactly. A big upgrade from you guys. Seriously, let's talk about something else. Or please, be like the giant mole on my face and don't say a word. And what did you say?
You heard.
How about we talk about the random motion of molecules and their collisions with a surface, creating an observable pressure on that surface.
Oh, hell no.
Fine, we can talk about something else.
Okay, let's talk about the combined gas law.
Oh?
Yeah, the combined gas law that combined Charles' law, Boyle's law, and Gay-Lussac's law. Hence, the combined gas law. The way to know which equation to use is whether combined or ideal gas law. You have to look at the information given to you. For example, if you get a problem with two or multiple things, you know you're going to have to deal with the change of something, so you use the combined gas law, which is P1V1 over T1 equals P2V2 over T2.
Look.
Really? What else?
If you have limited information and you have all parts of the equation except one, then you know you use the ideal gas law, which is PV equals nRT. In the combined gas law, you won't always have all the parts. Something could be missing, whether it's P or V or T. If you're missing a part, then you continue without it, combining only two of the equations out of the three.
And you wouldn't happen to be getting that info from your iPod, would you?
I would never. What? I think science is boring. Why? Why would I ever do that? Oh God, no. I only say what I know.
Really? Then what's that in your hand?
Nothing. This is just my iPod that's off, and I've not been on the internet at all. I just checked my Facebook.
Really? Can you show us an example?
Yeah, yeah, sure. Why not? Okay.
Where did you pull that out from?
I don't know. Magic. So, anyways, this is our problem. 6.2 liters of an ideal gas are contained at 3.0 atm and 37 degrees Celsius. How many moles of this gas are present?
That's a good question.
We insert the values. For example, our P is 3 atm, our volume is 6.2 liters. We don't know what our N is because that's what we're trying to look for. Our R is 0.0821, always and forever, a very magical number. And our T, 37 degrees Celsius, and you always have to add 273 Kelvin to make it into Kelvin. And that gives us 310. So we plug it in. PV equals nRT. So you multiply your pressure times your volume. 3 times 6.2 is 18.6 equals your R and your T. 0.0821 times 310 equals 25.451. Now, there's like an invisible end there. We're going to divide both sides by 25.451. And when we do that, we get 0.73, our magical number of moles.
Good job. See, you do know stuff.
Okay, but since we listened to you now, we have to talk about the random movement of particles in gases and stuff.
Alright, I'm prepared now.
What? Anyways, let's begin.
The kinetic molecular theory is when the gas particles are in constant, rapid, random, or straight line motion.
Look, you can see the gas jumping up when you pour the soda.
Oh yeah, look at that. I said look at that, not throw it at my face.
Oh, sorry. I understood something completely different.
Anyway, since there are no attractive forces between gas molecules, the conductions are completely elastic, which means no loss of energy. The gas particles occupies negligible volume, and their temperature are connected to Kelvin.
Next is diffusion, which is the rate of gases mixing. The random movement of gas molecules causes diffusion. If the temperature increases, so does the diffusion rate, and the smaller the molecules, the faster it will go.
Okay. Can we talk about something that's not boring and sciencey, like food?
Alright.
We didn't even talk about water.
I know, but I wanted to do that.
Right, I bet.
Anyway, what do we talk about?
Anyways, I heard Christian Castro announced he was gay.
Too bad, he was such a player with the girls.